Hello everyone, welcome back to CFD College. I'm Ashkan and this is another video on Fluid Mechanics 1. In this video we are going to solve 10 or 11 problems regarding dimensional analysis and modeling. I hope you enjoyed this video. This chapter is one of the easiest chapters in fluid mechanics. But it's a bit, time consuming to solve these problems, and you have to be careful. Otherwise, you can easily make mistakes. First of all, if you like these videos, and I have other videos on numerical simulations using ANSYS Fluent, please subscribe the channel and share these videos with your friends and give us a thumbs up. Let's jump to the assignment E. We have, I think, 10 or 11 problems. So, first problem, problem number 4. It's easy, it's super easy actually. I think the first two problems are super easy. The Reynolds number, rho VD over mu, it's a really important dimensionless number in fluid mechanics. You will see it again and again and again, and if you continue your education in fluid mechanics, you will see this number, this dimensionless number, a lot, and you have to know the meaning of this, the concept behind this number. It's a very important parameter in fluid mechanics. Verify that the Reynolds number is dimensionless using both FLT system and the MLT system for the basic dimensions, and determine its value for ethyl alcohol flowing at a velocity of 3 meters per second. So velocity is 3 meters per second through a 2-inch diameter pipe. So D is 2 inches. This D, you might see Reynolds number with this formula, rho VL over mu of if you work on airfoils, you may see this rho VC over mu. C is chord of the airfoil. This is chord length. So L, C, or D, actually it's the characteristic length of the problem, which is depending on the it depends on the problem you are studying. For example, on airfoil, the characteristic length is the chord length. For flow inside pipes, it's diameter. For flow over a flat plate, it's the length of the plate. So it varies regarding the problem. Okay, now let's solve this problem first. As you know, the dimension, the unit of rho in FLT is F T square over L to power 4, and in MLT is M over L cubic L. Actually, it's kilogram per cubic meter. Velocity is L over T in both systems, and diameter has the unit of length. So first, in MLT system, Reynolds number equals rho VD over mu. Rho, the unit is F T square over L to 4. V is L over T. D is length. Oh, I forgot to mention the viscosity. The dimension of viscosity is F T over L square in FLT system, and M over LT in the MLT system. So here we have F T over L square. And as you can see here, we have F, so in the numerator and the denominator, so they are cancelled. T square, T and T, so it's cancelled, and we have L square here, L to power 4, L to power 2, so all the units are gone. It means that this Reynolds number is dimensionless. In MLT system, Reynolds number equals rho, which is m over cubic length, v L over t, d is length, the unit is length, and here we have f over lt, m over lt. So m, with this m, we have t here, and L square. With this one we have cubic L, and here we have cubic L. So again we have no dimension for Reynolds number. It's easy, as you can see. For ethyl alcohol, viscosity is 1.19 10 to minus 3 Newton second over cubic meters, and density is 789 kilograms per cubic meter. So Reynolds number equals rho Vd over mu. Rho is 789 kilograms per cubic meters. Velocity 3 meters per second, and diameter 2 over 12 feet, and you have to convert feet to meter. 0.3048 meters equals 1 foot, and the viscosity is 1.19 10 to minus 3 Newton second per square meter. Okay, now you can find Reynolds number, which is equal to 1.01 10 to power 5. Here we should have square meters. Let's go to the next problem. Oops. Let me some time, give me some moments to fix this. This is the second problem, problem number 5 of chapter 7. For the flow of a thin film of a liquid with a depth of h and a free surface, two important dimensionless parameters are fluid number, velocity over square root of gh, and the Weber number. Determine the value of these two dimensionless groups for glycerin at 200 at 20 degrees centigrade, following with a velocity of, so we have velocity 0.7 meters per second at a depth of 3 millimeters. So h is 3 millimeters. Okay, for glycerin we need density, which is 1260 kilograms per cubic meter, and surface tension, which is 6.33 10 to minus 2 Newton per meter. So fluid number equals velocity 0.7 meters per second over square root of gravity 9.81 meters per second square times 0.003 meters, which is the h. So fluid number equals 4.08, and Weber number equals rho 1260 kilograms per cubic meters times velocity 0.7 meters per second square times h 0.003 meters divided by sigma, surface tension 6.33 10 to minus 2 Newton per meter, and the Weber number equals 29.3. As I mentioned, these problems are easy and you don't have problem to solve this. The first problem number 6, the Mach number for a body moving through a fluid with a velocity v is defined as v over c. So Mach number is v over c. Velocity over the sound speed. C is the sound speed in the fluid, or for example in any gas or liquid. This dimensionless parameter is usually considered to be important in fluid dynamics problems when its value exceeds 0.3. So when we have Mach number greater than 0.3, it means we have compressible fluid. So in these flows, we have compressible flows, not fluids. So we have compressible flow, which means rho is a function of pressure, and most of the times we solve these problems with the assumption of ideal gas. Law. Okay, what would be the velocity of a body at a Mach number of 0.3 if the fluid is air at standard atmospheric pressure and 20 degrees centigrade? So Mach number equals v over c, and for air at steady, standard temperature and pressure, which is ambient atmospheric pressure and 20 degrees centigrade, speed of sound is 343.3 meters per second. So from this we can understand that velocity equals Mach number times c. Mach number is 0.3 Speed of sound is 343.3 meters per second. So the velocity equals 103 meters per second for part A. For part B, we have water at the same temperature and pressure. So for water at 220 degrees centigrade, speed of sound is 1481 near 1500s. So velocity equals 0.3 times 1481 meters per second. Therefore, velocity equals 444 meters per second. This was also super easy. Now we have a good problem. This is the type that you might see in the exams. At a sudden contraction, so we have a contraction. This is the pipe, and we have a contraction. Diameter changes from D1 to D2. So here we have D1, here we have D2. Pressure drop delta P, which develops across the contraction, is a function of, so delta P is a function of D1, D2, velocity in the larger pipe. So here, for example, we have velocity V. The fluid density and viscosity, rho and mu. Use D1, V, and mu as repeating variables to determine a suitable set of dimensionless parameters. Okay. So in these problems, we should first make a list of variables and their units. Delta P, we have delta P. The unit is F over L square. D1, D2, unit is L for both. Velocity, the unit is L over T. Density, the unit is F T square over L to power 4. And the last one, mu, the unit is F T over L square. So we have 6 quantities, m is 6, m is 6, n is 3, f, l, and t, we have 3 units. So we should have 3 dimensionless groups, pi 1, pi 2, and pi 3. And we have to find them. So we should pick D1, V, and mu. So since n is 3, we should pick 3 repeating variables. Here we should pick D1, velocity, and mu. Okay, now we can solve the problem. So pi 1 equals, we start from delta P. Delta P, the unit is F over L square. So we have force in mu, so we should put it here, F T over L2. Now F is gone. We have to deal with T. We have a T here, so we need L over T. Now T is cancelled, and we have velocity here. And to deal with this square L, we need L in the numerator or 1 over L in the denominator, which means we need d1 to the power of -1. So pi 1 equals delta p d1 over mu v. Next one is d2. It's easy. Pi 2 equals d2. The unit is L, and if we put d1 here, we have the dimensionless group. So pi 2 equals d2 over d1. And the last one, pi 3 equals, we should pick rho. So the last one is rho. The unit is f t square over L4. We should put viscosity to cancel ft over L2. So f is gone. We need t time. So I should have t over L here, which means velocity to power -1. So v -1. And we need another L here, this one, which means d1 to power -1. So d to the power -1. So pi 3 equals rho v d over mu, which is Reynolds number. And now you know it. So the final answer is pi 1 is a function of pi 2 and pi 3, which means that delta p d1 over v mu equals, it's a function of d2 over d1 and rho v d1 over mu. That's it. And here we have another question. Why would it be incorrect to include the velocity in the smaller pipe as an additional variable? Well, you know it. It's obvious because the flow rate is constant. So Q1 equals Q2, which means V1 A1 equals V2 A2, which means V1 pi d1 square over 4 equals v2 times pi d2 square over 4. So actually by having v1, d1 and d2, we have v2. So it's not an independent variable. It depends on those three. That's the reason we can't assume that as an additional variable. Next one, problem number 10. Water sloshes back and forth in a tank as shown in the figure below. The frequency of a sloshing, omega, is assumed to be a function of, so omega is a function of the acceleration of gravity g, the average depth of the water h, the length of the tank L. Develop a suitable set of dimensionless parameters for this problem using G and L as repeating variables. Okay, so the first step, making the list. we have four quantities: omega, gravity, h, l. The unit for the omega is actually over time, so 1 over t. Gravity is length over t square. H and L are length. So we have four quantities, m equals 4. We have two different units, n equals 2. So we will have two dimensionless groups, pi 1 and pi 2, and the repeating variables should be gravity and L. So we should start from omega. Omega equals here we have here we have omega pi 1 equals, here we have omega, the unit is 1 over t. To cancel this t, we should use gravity. So but since we have t here and t square there, we need to use the square root. So actually we need L over t square to the power of 1 over 2. It's a square root. It's a square root of gravity. So here we have a square root of gravity. Now t is cancelled, but we have L to power of 1 over 2. So we need 1 over L to the power of 1 over 2, which means the square root of 1 over L. So here we have a square root of 1 over L. So pi 1 equals omega times square root of L over G. This is pi 1 actually. And pi 2, so gravity and L are repeating variables, and we only need to find the pi 2 based on h. So here we have h, here we have the unit which is length. It's easy, we need length here, which is L. So this is pi 2. So pi 1 omega over L over G, remember this is the final answer, you have to write it down, is a function of pi 2 h over L. This is the final answer that you have to write down in your papers in the exam. Don't forget that. Problem number 12 of chapter 7. The pressure rise dP across a pump can be expressed as delta P is a function of diameter, impeller diameter, fluid density, rotational speed, and the flow rate. Determine a suitable set of dimensionless parameters. So first, making the list, delta P, the dimension is F over L square, diameter is L, the unit is L. For the density, the unit is F T square over L to power 4. For omega, it's 1 over T, the unit I mean. And for the Q, flow rate, is the unit is length, cubic length over time. Actually it represents cubic meter per second or cubic feet per second. So we have 5 quantities, 3 fundamental units. So we will have 2 dimensionless numbers, pi 1, pi 2. We should pick 3 of these quantities as a repeating variables. So I pick diameter for L, omega for T, and density for F. So pi 1, now we know that D, rho, and omega are gone. Pi 1 equals delta P over, here we have F over L square as the unit. So we should pick rho here, F T square L to the power 4. Now we need to cancel the time. So we need 1 over T square, which means omega square. And we have L square because we have L square here, L to power 4 here. So we have L square. If I put L square here, which means D square, we have found our first dimensionless group. The second one, pi 2, equals, we should deal with Q. The unit for Q is L to the power 3 over time. So we have to deal with L and T, so there is no need to put rho in the denominator or in the numerator. So first for L, we need L to the power 3 here, which means D cubic diameter, and we need 1 over T, which means omega. So it's super easy. So as you know, the final answer would be pi 1 delta P over rho omega 2 omega squared D square equals a function of Q over cubic diameter times omega. Next problem number 16. A cone and a plate with commuter consist of a cone with a very small angle, alpha, that rotates above a flat surface, as shown in the figure below. The torque required to rotate the cone at an angular velocity of omega, for example, is a function of, so T is a function of radius, the cone angle, alpha, the fluid viscosity, mu, in addition to omega. So we have omega also. With the aid of dimensional analysis, determine how the torque will change if both the viscosity and angular velocity are doubled. So we have to find the relationship between torque and viscosity and omega, and then we can find out if we double them, what happens to the torque. So first, make the list. Torque, the unit is FL. If you don't know this, as you know, torque is equal to RF. So F is force, R is length. The second one is R, the unit is L. The third one is alpha. Alpha is dimensionless, so there is no dimension here. Actually, it can be radians, but it's not F, L, or T. And the fourth one is mu f t over L square. The fifth one is omega 1 over t. So m is 5, n is 3, f, l, and t. So m minus n equals 2. So we have pi 1 and pi 2. So pi 1, sorry, we have to pick 3 of these quantities for as repeating variables. We should pick omega, mu, and r. Certainly we can't pick alpha because it hasn't unit, and we can't pick torque because we want to investigate that. You can pick torque, but it's not usual. So pi 1 equals, we have torque F times L. So we need to cancel F. It's obvious that we need mu here. F t over L square. Now F is gone. We have t here. So if I put 1 over t, the t is gone. So omega. And for L, we have only L here. No, here we have L square. So basically, we have L, cubic L in the numerator. So we need cubic L, which means R to the power 3. And what about pi 2? We should go for the next quantity, which is alpha. And alpha is dimensionless. So pi 2 is alpha. You don't need to find anything. So the final answer, pi 1 t over mu omega cubic r, is a function of alpha. So if alpha is fixed, it means that we have this relationship. Actually, it's not like this. So let me erase this. Let's say in another way, t equals mu omega r to the power 3, and an expression for alpha. We don't know it, but since alpha is fixed and also radius, it doesn't matter what is f of alpha, function of alpha. So we wanted to know that if we double the viscosity and angular velocity, so mu and omega are doubled. If mu and omega are doubled, we have a linear relationship for each of them, between each of them and torque. So if mu and omega are doubled, it means that t will increase by a factor of 4. And for example, if we double radius, only radius, t will increase by a factor of 8. So this is how you can answer these kinds of problems. Let's go to the next problem, problem number 54. When a small particle of diameter d are transported by a moving fluid having a velocity v, they settle to the ground at some distance L. So here velocity, length L, and height h. After starting from a height h. The variation in L, in the length, with various factors is to be studied, with a model having a length scale of 1 to 1 over 10 or 1 to 10. So we know the scaling. Now we are comparing the prototype and the model. Assume that L is a function of h, diameter, velocity, specific weight, and viscosity. Specific gamma is particle specific weight, mu is fluid viscosity. The same fluid is to be used in both model and prototype. It means that mu m equals mu. Gamma of the model is 9 times gamma of prototype. So gamma m equals 9 times gamma. If v velocity equals 50 miles per hour, at what velocity should the model tests be run? Okay, so we want to find in part A, we know velocity for the prototype is 50 miles per hour, and we want to find the velocity in our model. And during a certain model test, it was found that L for the model is 0.8 feet. So Lm equals 0.8 feet. What should be the predicted L for this test? And we should find L. Okay, good. Now we should firstly find the dimensionless groups, and then we can solve the problem. So first we need to find the dimensionless groups. Let's do it. So first, making the list L. Let me make the list here. It's pretty easier. L, the unit is length. H, the unit is L. Diameter, the unit is L. Velocity, L over T. Gamma, gamma is rho G. Gamma equals rho G. Rho F T square over L to power 4. Gravity is meters per second square, L over T2. So gamma has the unit of F over L to power 3. And the last one, mu, viscosity, Ft over L square. So we have 6 quantities. M is 6, N is F, L, and T, 3. So here we have 3 dimensionless groups, pi 1, pi 2, and pi 3. And we have to pick 3 of these as repeating variables. So H for length, V for T, and gamma to have force. Yes, I think it's good. So now we can find pi 1, pi 2, and pi 3. So pi 1 equals, H is gone, is picked actually, V is picked, gamma is picked. So the first one is L, and you know it's easy because we have h for this unit. So pi1 is easy to find. Pi2, the next one is diameter, and actually it's easy too, because you know the unit is L and we have h for the unit, for this unit. The last one we should deal with mu, f t over L square. So we need f, we should pick gamma, f over L to power 3. Next should be t. So we need t in the denominator, t over L, which means v to power -1. And then we need L2 here, L square, I mean. So h to power 2. So pi3 is mu v over gamma h to power 2. So now we have our three dimensionless group. So we know L over h equals, actually it's a function of diameter over h and mu v over gamma h square. So for the similarity, all these three should have the similarity. In part A we have velocity. It's obvious that we should use pi3. So mu m vm over gamma m hm square equals mu v gamma h for the prototype. So vm equals gamma m over gamma mu over mu m and hm over h square times velocity. We know that mu m equals mu, so vm equals gamma m over gamma, so 9 gamma over gamma, or let's say 9. The ratio of viscosities is 1, and hm over h is 1 over 10. When you are told that the scaling is 1 over 10, it means that, for example, hm over h equals 10. Sorry, equals 1 over 10. The model mostly, if I want to be correct, or maybe all the times, the model is smaller than the prototype. And we have the velocity. So the velocity was 50 mph, miles per hour. So Vm equals 4.5 miles per hour. For part B, we should use this one because we want to study L and we know the scaling, I mean h. So Lm over hm equals L over h. So L equals h over hm times Lm equals 10. Here we have h over hm times 0.8 feet. So L equals 8 feet. So let's jump to the next one. I think we have three more questions. Problem number 55. A thin layer of an incompressible fluid flows steadily over a horizontal smooth plate, as it's shown in figure below. The fluid surface is open to the atmosphere, so we have a free surface, and an obstruction here, having a square cross section, so it's a square, is placed on the plate as shown. A model with a length scale of 1/4. So the scaling is 1/4. It means that D or L, whatever length characteristic you have in the problem, dm over D equals 1/4. A fluid density scale of 1, so rho m over rho is 1, is to be designed to predict the depths of fluid. The depths of fluid, okay. Gamma along the plate. I think it should be y, not gamma. Okay, whatever. Assume that inertia, gravitational, surface tension, and viscous effects are all important. Okay. What are the required viscosity and surface tension scales? If you know Froude number, which is equal to V over square root of GL or GD or GH, I don't know, is a ratio of inertia to gravitational force. So inertia force over gravitational force. Reynolds number, which is rho v d or L over mu, is the ratio of inertia and viscosity. Viscous forces. And what else? Oh, sorry. And Weber number, which is rho v square L or D, I don't know, over sigma, is a ratio. Actually, it's important where we are dealing with surface tension, but it's a ratio of inertial force and surface tension. So we should maintain similarity. We should be sure of maintaining similarity for these three dimensionless numbers. So let's start with Froude number. So Vm over square root of Gm, for example, Lm or Dm equals V over square root of Gd. So since gravity is fixed, Vm over V equals the ratio of Dm over D. Okay, but we need to find the ratio of viscosity and surface tension, so this might help us. Next, go to Reynolds number similarity. Rho m Vm dm over mu m equals rho v d over mu. So from this we should find the scaling for viscosity. Mu m over mu equals rho m over rho vm over v dm over d. And now, since we have the scaling for the length and density, but we don't know anything about the scaling of the scale, the ratio of velocities, we should use this star equation. So it equals rho m over rho square root of dm over d times dm over d. So we have 1 times 1 over 4 to the power of 3 over 2, which means 1 over 8, or 0.125. And from Weber number similarity, we should find the scaling for the surface tension. So rho m vm square dm over sigma m equals rho v square d over sigma, which means that sigma m over sigma equals rho m over rho vm square over v square dm over d. So the ratio of densities is 1, and we have the star equation, so it equals rho m over rho dm over d and dm over d. So we have 1 times 1 over 4 times 1 over 4 equals 1 over 16 equals 0.0625. So now we have the ratio, actually the scale for the viscosity and for the surface tension. Next problem number 61. The pressure rise delta P across a blast wave, as shown in the figure below, is assumed to be a function of the amount of energy released in the explosion. So delta P is a function of energy, air density, speed of sound, so rho c, distance from the blast d. A, put this relationship in dimensionless form. Okay, so for part A we should find dimensionless numbers. In part B, consider two blasts: the prototype blast with energy release E and a model blast with 1 over 1000 the energy release. So we know EM equals 0.001 E. At what distance from the model blast will the pressure rise be the same as that at a distance of 1 mile from the prototype blast? So actually we have D, which is 1 mile, and we have to find dm, for example. Okay, as you know, the first step is to find the suitable dimensionless numbers. So first, making the list: dp L over L, F over L square, energy FL, the third one is rho F T square over L2 power 4, speed, sound speed, L over T, and the last one, which is D with the length of L. Okay, so we have 5 quantities. M is 5, n is free, so we have two dimensionless groups, pi 1 and pi 2, and you have to find them. So we should pick free quantities, rho, c, and d. So pi 1 equals delta p over something. The unit is L or F over L square. So we should use rho here to cancel F. F t square over L to power 4. And if you pick c square, you will have L square over t square. So t is cancelled, and also the length. So this is the first one. The second one is the one which is related to energy. F times L. So I should pick rho here. F t square over L to power 4. Now F is gone. And for t, we should have L over t square. So c square. And now we need one more length here. No, sorry. L square. This means L to power 5. So we need L to power 3 here. D to power 3. Okay, so we know that delta P over rho C2 equals, actually it's a function of E over rho C square cubic diameter. So this was part A. For part B, similarity, we need to use similarity since we are dealing with energy and D. It's okay if we use the second dimensionless group for the similarity. So EM over rho m cm square dm to the power 3 equals E over rho c square cubic d. So if density is constant and also the speed of sound, since we have air in both cases, in the actually for the model and the prototype, it means that dm power 3 equals em over e times d to power 3 equals 0.001 times 1 mile to power 3. So dm equals 0.1 mile. And now we can find the pressure drop. So d delta p for the model over rho m cm square equals delta p over rho c square. So since rho and c are the same, it means that delta p m equals delta p, but you should remember that the diameter for the model is 0.1 mile. So we have this condition at dm equals 0.1 mile. Okay, now let's solve the last problem, problem number 66, sorry. 66. The drag on a sphere moving in a fluid is known to be a function of So the drag force D, D or FD, both are okay. Let's start with FD, drag force, is a function of sphere diameter, velocity, viscosity, and density. So FD is a function of diameter of the sphere, velocity of the fluid flow, and rho and mu. Okay, laboratory tests on a 4-inch diameter sphere, so dm equals 4 inches, were performed in a water tunnel, and some model data are plotted in the figure below here. For these tests, the viscosity of water was, so mu m equals 2.3 10 to minus 5 pounds per pound second per cube square feet, and the water density was, so rho m equals 1.94 slugs per cubic feet. Estimate the drag on an 8 feet diameter balloon, so D is 8 feet, moving in air at velocity of, so V, sorry, here sphere moving, here I said I think the velocity of the fluid, it's the velocity of the sphere. Sorry for that. So velocity is 3 feet per second. Assume the air to have a viscosity of, so mu equals 3.7 10 to minus 7 pounds second per square feet, and a density of 2.38 10 to minus 3 slugs per cubic feet. So actually we have everything. We just need to find the dimensionless numbers, dimensionless groups, and then maintain the similarity to find the drag force on the prototype, which is a balloon. Finding the dimensionless groups is similar to one of the problems I solved in tutorials. In tutorial number 10, it's the same problem. So I refer you to that video if you want. If you have problem, you can see that video of tutorial 10. So if you do that, you will see drag force over rho v square d square is a function of Reynolds number rho v d over mu. So for solving this problem, as you know, we have similarity for both these numbers. So from Reynolds number similarity, rho m vm dm mu m equals rho v d over mu. Okay, so first we should find velocity, because we have density and viscosity for the model and the prototype, and we have the diameter for both, but we don't know the velocity for the model. So Vm equals mu m over mu rho over rho m d over dm times velocity. So mu m is 2.3 10 to minus 5. I don't write, let me don't write the units because they are the same. 3.7 10 to minus 7. The ratio of densities 2.38 10 to minus 3 and 1.94. 8 feet over 4 inches. Don't forget to do the conversion, divided by 12, and the velocity is 3 feet per second. So Vm equals 5.49 feet per second. Now we should go for the similarity of the drag coefficient. It is called drag coefficient. So FdM over rho m Vm square dm square equals Fd over rho v square d square. So velocity is 5.49. Actually, it's near 5.5. We should use this chart. Here is 5 and here is 5.5. And for this, you can find the model drag. Near here is 1. So for example, at velocity 5.49 feet per second, the drag for the model equals 1.3 pounds. So now we can solve it, because from this equation we know that Fd equals rho over rho m v square over vm square d square over dm square times drag force of the model. So Fd equals 2.38 10 to minus 3 over 1 over 94. The units are the same. Velocity 3 feet per second square, 5.49 feet per second square, 8 feet, 4 over 12 feet square, don't forget that, times Fdm, which is 1.3 pounds. So Fd, the drag force of the balloon, equals 0.274 pounds. That's it. This is the end of this video. I hope you enjoyed it. If so, please share these videos with your friends and give us a thumbs up. Don't forget to subscribe to the channel. I have many other useful videos on numerical simulations using ANSYS Fluent. Until the next video, take care of yourselves and bye bye.